Thanks so much, Rob, for the nice introduction, and thanks all for having me today. So indeed, as Rob introduced, I will be telling you about our worldwide AI for Good community called Footprints AI. I will be telling you what we do, who we are, how we approach our projects. Then I will freight train you to a couple of the different types of projects that we have solved in the past to give you an idea of the types of things you can do by applying AI for good. And then we're going to do a deep dive, a technological deep dive in one of my favorite challenges and definitely the cutest challenge that we have solved, AI for Seals. So a short introduction first from my side. I studied computer science in Eindhoven University, 2011 already. I was the chairman of Quiz 14-15. That's also where I know Rob from. We were fellow chairmen back in the day. I was the first generation of the data science master in Eindhoven. Around this time, all the data science hype and AI hype hit all the universities. So they were like, we have to have these types of education. And as a student advisor to the departmental board back then, I helped setting up the first bachelor's and master's specializations in deep learning and machine learning. After that, I did software architecture and setting up a data science team at a software consultancy company. And here I ran into the first issues. I noticed that everything I learned in university was mostly about modeling, some of the mathematics behind these types of models, and all the other stuff were like neat notebooks that you could load the data sets into your RAM and then apply some AI to. And this is actually a lot very, very far from how AI works in industry. So as a computer scientist, I was able to learn these things on the job because a lot of these concepts lie very close to computer science. But once I was growing my data science team, I ran into this problem more and more often, especially with people that have different backgrounds, for example, industrial engineers or biomedical engineers that specialize in data science later on. I learned that they really didn't have the experience necessary to apply AI in practice. And this is how I got to discuss together with my co-founder, Buster, how can we solve this problem? How can we teach people how to apply AI in practice? And this is the seed of Footprints AI, of which I'm now the CTO. Last thing about myself is that besides all these things, I'm also just the common nerd. I play with Raspberry Pis and LEDs at my home. I automate everything to Chinese domotica, setting up overly complex application that's no one ever going to use, and I only get to break every once in a while and then spend hours debugging. And lastly, I like to select software and hardware for friends when they need to build a new rig, then they always give me a call. So I'm your typical computer nerd. But more about Footprints. So at Footprints, we are the global AI for Good community, and our aim is to educate and apply AI for good. And our main mechanism in doing so are our AI for Good challenges. So our AI for Good challenges are projects for which we collaborate with organizations worldwide. So we're always searching for organizations, which can be companies, governments, corporates, startups, doesn't really matter, as long as they have a data set and a problem they would like to solve, of which the project goals align with the Sustainable Development Goals of the United Nations. And this is how we formalize AI for Good. So once we've identified such a project, we crowdsource experts from our community. So these are experts that are either very familiar with the type of AI that we're going to need in the project, or they are domain experts in the type of project that we're solving. And we combine these with engineers from companies, junior, media, but also senior engineers who would like to learn how to apply AI in practice and would like to learn how to apply state-of-the-art AI. So these are our AI for Good challenges, and I'm going to tell you all about them in a second. But as mentioned, this is not just a way of doing AI for good, it's also a way of learning AI for good. And that's also why we offer an accreditation system as part of our platform, where once you partake in such a challenge, you get accredited on all the skills that you've shown in a challenge. So it's not a general certificate that says, hey, you did this challenge and now you know pandas. But it's really dependent on the skills that you showed in the challenge, and this is also where you get accredited for and get certified for. So we do these challenges with tons of types of organizations, as I already mentioned. Here are some of the organizations that we collaborated, Stanford, ESA, Yachts, Huawei, Cornell University. But more interesting is, of course, the type of problems that we solve. So first of all, I'm going to jump straight into the right now hype, the Gen AI. We work a lot with large language models. And these are two challenges, one together with a startup called Jay-Z and one together with Metabolic, which is a consultancy firm in Amsterdam. And both had a similar problem, which was we want to estimate the carbon impact of a person, in case of Jay-Z, or of a company, in case of Metabolic. And we want to do this based on their financial transactions. Since, as you can imagine, if you have a company, you pay a lot of invoices. There's stuff that you buy. And on these invoices, there's this short rule, often just 4 or 5 words long, that describe the product that you have obtained. And then it has a number, how much it cost, and a number of the quantity of the product. Our goal was to translate this line into a carbon emission, which is very difficult. The reason that it's so difficult is that it's just 4 or 5 words. And if someone would have come to me 3 years ago and would have asked Sako, can you solve this issue for me? I would have answered the question with, no, I can't. I need a lot more data about these products to be able to estimate the type of product. You have to imagine that it simply says packaged pork in German or something like that. These are the types of variations that you work with in these invoices. And there's simply not enough information to estimate what that is. But this is where large language models comes in. These types of models do not only have the information that is in the invoice, but it also has a huge context as part of the model itself. So these models have an understanding of the world ingrained in their embedding, and therefore they know if this invoice is in German, the invoice address is from a certain region in Germany and it's mentioning packaged pork, then it's very likely a special type of ham that they make there in large quantities. And these types of contexts that are part of these models allow us to actually make this translation directly. So we applied large language models to translate these different invoice, but also personal transactions to actually product types, and from there to carbon estimates. And in that way you can very quickly, based on your bank account or based on the financial system of a company, calculate the full carbon impact of such a company. So this is how we applied large language models. But we also do a lot in the space engineering side of things. And then we're mostly talking about using geospatial information systems and remote sensing. So we're talking satellites here. We did one of those projects together with ESA, where they basically said, hey, we have about 50 satellites in the air. They all measure different kind of stuff. Like some of them just measure RGB camera feeds, but other are radiographic, ultraviolet, far and near infrared, and all these different spectra. What can you measure based on all these different types of sensors? So we did coral bleaching, deforestation, flooding of rivers, dying of rivers, urbanization, and all these things that we could detect based on the satellite image in automatic ways, such that we can plot over time whether a forest is decreasing, increasing, and whether rivers are dying. Something else in the same space we did together with a startup in France, Vortex AI, and this was about flooding. So it's, as we have the problem here in the Netherlands as well, that our rivers overflow, this is also a very common problem in France. So this organization has sensors throughout the river. And what they want to do is like, hey, I have measurements at the start of this river. I want to know the water level at the end of the river. This is obviously to be able to predict how high the water level is once it will go over the dikes, and then be able to warn people in advance to evacuate once the water level is going to be too high. So we set out with this goal, and what every data scientist does, if you give them this data set, oh, let's try the newest recurrent neural networks and all this fancy stuff that's out there. Well, this challenge is a perfect example of that is not always the solution. In this case, we ended up with a profit algorithm, which is an algorithm based on your classical type of statistics like moving average and seasonal moving average. Some of you might have learned about this stuff in your statistical courses, which is ancient technology, right? We're talking about designed in the 1920s or something. These algorithms ended up being most accurate. They were so accurate that we could predict 6 hours in advance with an accuracy of 90% how high the water level was. And 6 hours is a lot in terms of being able to actually evacuate a region. Then in healthcare is also a space where we commonly do projects. And one of the obvious things is, of course, the radiology space. Here we have things like x-rays of lungs, where we automatically segment the lung part such that the doctors don't get distracted by all the other things that are part of the image, but also to de-identify them. And we also do things like patient deterioration prediction, which based on the blood work of several patients, you try to predict, hey, in the near future, is this patient going to need intensive care? Might they die, or are they going to stay stable? And one of my favorite projects in this space is AI for preterm babies. Some of you might know that sepsis infection, which is a bacterial infection which you commonly get inside of the hospital, is the #1 cause of infant death in the Netherlands. And we built a system, again, based on the blood works of these infants to predict whether the risk of sepsis was high in certain infants, and therefore they could apply antibiotics before the infection took hold and might have caused a death. So these are the things you can do with AI. We also have more industrial cases where we look together with Rijkswaterstaat if we can detect oil spills, and the oil spills that you will be familiar with are known as sea spills. These are the things that you see in the news. A large oil tanker is leaking somewhere in the bay or whatever. This is a huge problem. These oil spills are enormous, but they are also very rare. However, harbor spills are not. Harbor spills happen every other day in the Netherlands. So every other day there's somewhere in a harbor in the Netherlands, there's a spill, and Rijkswaterstaat needs to clean that spill. And to be able to do this, they need to know the type of oil, they need to know the size of the spill, the depth of the oil in the water, and all these parameters are very important for them to estimate the type of cleanup that they need to do, and then also if they need to escalate the organization. So based on drone imagery, so drones flying over these harbor spills, we're able to estimate all these parameters for them as an input to then plan an intervention. Furthermore, we worked on the predictive maintenance of windmills. As you might not be familiar with, windmills, you want to measure the vibration of the blades to be able to do predictive maintenance, but you can't just put your classical hardware in there, because windmills get struck by lightning all the time. So if you just put a normal microcontroller in a wind blade, it will get fried instantly the moment that it hits the wind blade. So together with a startup in Eindhoven called Taruka, they are developing a special completely photonic sensor that both is photonic electronics but also a photonic sensor part that they can, based on light, can measure the vibrations, and we build algorithms based on their experimental data to detect where in the wind blade the damage is and the size of the damage, such that in this case they can plan maintenance the moment that the windmill is likely out of use due to low winds. And then lastly, in terms of categories, ecology. We do a lot of challenges in the space of ecology. I guess that's because it's a personal interest of mine, or maybe because we can still film animals without it becoming a problem with the GDPR. So we worked on, together with Stanford and Cornell University, we worked on AI for forest elephants, where they have an array of microphones in the Central African rainforest. And the goal is to hear the elephants, but also hear the poachers. So these recording devices are continuously recording as part of this grid and sending back the data of the audio. Up to us was the goal of detecting elephant rumbles in that noise, such that you can localize the elephants in the space and can also track their behavior and movement. And this way you can also see when they are doing something weird, which might be caused by poaching activities. And on the other side, we were able to detect both vehicle noises, which are again often poachers, and gunshots, which are very obviously poachers. This data together, we built several algorithms that were able to analyze these spectrograms and then be able to send back signals to the rangers. And then lastly, for my quick examples, is AI for seals. But that's actually the ones that I'm going to tell you in detail about, because this is one of my favorite challenges, because it's the cutest challenge that we ever solved. So let's start with the problem, right? AI for seals, what's this about? We're talking specifically in this case about harbor seals in the Hudson Bay. And why are we so interested in identifying these specific seals? Well, seals are what they call a keystone species. And a keystone species is a species that's so central to the ecosystem there that it's a very good indicator of the health of the entire ecosystem. Less seals, meaning unhealthy ecosystem. A lot of seals means a healthy ecosystem. So they are a proxy to measure the ecosystem and other animals in the ecosystem. This is why we want to track the identities and see how the population grows and shrinks over time. And we obviously also want to do this non-invasively. Like, we don't want to drag them out of the water, tag them with some GPS tracker that they will likely lose in a year or two, which is also very stressful for the animals, obviously. So what the researchers of Colgate University were already set out to do is 2 times a year they go on boats, do 3 weeks of making pictures of all the seals that they can find, and then they go back to the lab and have researchers, like real marine biologists that are experts in identifying specific seals, sift through thousands and thousands of images. Well, this is obviously a waste of their capacities, right? These are people that are full-on trained marine biologists. They can do very important conservationist work. Let's not have them look at cute seal pictures all day. This sounds nice, but after 2 days you'll be sick of it. So let's do some AI on that, right? Let's build an AI that's able to identify these seals automatically based on the pictures that they make. Little side note here, these 2 seals here, they are called Sako and Dorian is my colleague. So this is the best accreditation that I got in my life so far. After we finished this project, they named 2 seals after us. So this is what you can get by doing AI for Good Guys, a seal named after you. So the approach we took to solve this problem, first of all, face detection. You have this picture, tons of seals in there. What you want to do is clip out the face, right? You want to identify one specific seal. So you want to count how many there are, and you want to be able to do the identification on a very specific face. So once you detect those clips, you want to do the face recognition. Basically, you're going to compare it to all the other seals in your data set, and you're going to generate a top 5 of most likely candidates that are the same seals. This is, as of most projects, where you still have a human in the loop, right? We can automatically identify all these seals, but also to give the researchers trust that this technology works well, you want to give them feedback like, hey, with a confidence level of about 0.8, we know for sure that it's Clove the seal in this case and not Frosty the seal, but Frosty is also a likely candidate. And then lastly, we need an application. These are marine biologists. They don't know Python. They don't know programming. They don't know Dockers. They can't do any of this stuff themselves. We need to build some application around this to be able to solve that, to really solve the problem and make a serious impact. And this is also where it becomes very interesting, because all these challenges take only 10 weeks. The participants in the challenge, whom are about 30 to 50 people, they spend about 8 hours a week on this challenge. So with this capacity, in 10 weeks, we need to solve all these 3 issues. And we ended up doing it, and this is how we did that. First of all, detection. So everyone familiar with computer vision will know that detection is kind of a solved problem. There are so many very strong frameworks out there. YOLO, you only learn once, is one of the most famous in the space, but also VIT, faster RCNN. And there are many of these frameworks that not only have a model that can do the detection, but have complete software frameworks around you that help you with data augmentation, loading in the images, saving the results, retraining your images every once in a while. All this stuff is part of the framework that they deliver together with these models. And this makes making a detection algorithm really easy, right? You need basic Python knowledge to be able to do this, and you'll likely build a very capable model. So this is quickly to be solved. However, then you come into where AI in practice is actually what you need to learn. Because as a data scientist, you could say, hey, I can do this in half a day, which is theoretically reachable if you only have to deploy one of these models. But which of these seals do I actually detect? Right? So this one is just in the corner. Do I detect it? Like, do I need or want to detect that? A seal that's looking completely at the side. You can't see both eyes. There's quite a lot of identification going on in being able to see both eyes. And one that's like on a quarter. Do I keep that into the data set? And this is where the domain experience from the marine biologists also come in, but this is also where AI becomes real, right? Figuring out together with the client, hey, how do we need to solve this? Are you interested in the seals that are looking to the side? Can we ignore them? Do we have to clean the entire data set to remove all these examples? And this is in the end what in most challenges we actually have to do. We have to review large portions, if not all of the data, to correct the labels, to have both the requirements from the researchers plus the requirements or capabilities of the AI being able to combine. On top of that, obviously, you want to create as large as possible data set as you can, so you add in multiple different types of data augmentation, and then you run the object detection pipeline. So in the end, we tried, we ended up trying out 3 different models after the initial exploration, which were RetinaNet, YOLO v5, and YOLO v8, of which the YOLO v5 and YOLO v8 model performed best. So those familiar with AI will know what these statistics mean, but in the end, the precision here tells us about how many times we were correct in this sense, and the YOLO v8 was only 91%, but the recall is also a very important metric in terms of identification, and there YOLO v8 really outperformed the model as well with the MAP scores, where the MAP scores measure the overlap of the bounding boxes, aka how far the bounding box that you predicted and the bounding box that's really there, how far they overlap. So while 60 or 50% might sound like less, that does mean that at least 50% of the entire bounding box overlaps, and that's very indicative of the accuracy of the model. So that's face detection. As mentioned, easy part in terms of computer vision. Recognition, or re-identification as it's often called, is not. So what you want is a top 5 similarity, and this is a very hard problem to solve. There are many ways of doing this. So the most obvious one would be classification, right? We have a data set. In the data set there are 190 different seals. We take a classifier. For all I care, you take random forest, and you have them train on these things and put them in one of the categories. The problem with classification, however, is that if you add a seal to the data set, you will need to retrain the entire model. So this holds for convolutional neural networks and any type of classifier that you would want to use. You need to retrain the entire classifier. Another approach that you could do is cluster. So trying to cluster all points in the data set, and then you use similarity metrics or Euclidean space metrics to be able to decide whether points in the data set are close together, and close together in the data set in this case would then mean this is the same seal. And lastly, we have using a similarity metric based on some embedding that you compute. So these are some of the different ways that you could solve this problem, which all means completely different types of algorithms, and none of these is like solved in terms of state of the art. Where with face detection, if you use YOLO, you're quite sure that you're using about the best algorithm out there, and then it doesn't really matter if it's really the best of the best. But in this case, any of these 3 methods each have like 5 or 6 state-of-the-art algorithms that are tested, and then 5 or 6 more that are really just in the papers that you would need to implement by hand to see whether they might work better compared to the other methods. So this is a very unsolved problem. So we ended up trying 3 different methods here, which is a feature extractor combined with a classification step, a classifier of which we got the head of the classification layer and then use a cosine similarity, and metric learning. So I'm briefly going to go over these approaches and show you how they work. So the feature extractor that we ended up using is HOG. Feature extraction is a completely own field within computer vision. It's also quite an old field. It's used in robotics a lot. And basically the goal is build some algorithm, often handcrafted algorithms in this case, that try to detect unique features in the data set. So it's basically detecting stripes, figures, all these types of stuff in the data set. And then on top of that, you have these different features that they extracted from the image, and then you do a classification step. In this case, it's cascade gradient descent. The scores were quite okay. As you can see here, we have one score of 95%, but this does have the problem that you did a classification step and therefore had to retrain at least the classifier part, not the feature extractor in this case, whenever you expand on a data set. In case of the similarity metric, we basically just trained a classification algorithm, a convolutional neural network, EfficientNet B1 to be specific, but you basically take the entire classifier and then cut off his head. And what you have done there is first you train a classifier on your limited set of features, but your classifier will learn something about what seeliness means. And this seeliness is not something that we can comprehend as humans, but the near to last layer of the network will represent, in some way that we again do not understand, it will represent the seeliness of unique seals. And this embedding, as you call that then, you can use to then put into a clustering and measure the distance between different pictures, and then you are able to identify individuals using clustering metrics. Last one, metric learning. This is my favorite type of AI. I'm that type of nerd. I have a favorite type of AI. And this is detecting similarity. So what classifiers do, they are very strict in, hey, I need to have one of these 5 classes. However, metric learning works differently. They try to identify the space between examples, which is what this graph here illustrates. These are a data set of world leaders, and what you want to teach the algorithm is how to identify them. And what you do is you have one anchor. This is the base image that you're going to compare. You give one positive and one negative example. And what that does, instead of trying to guess whether it's the right or the wrong one, it will learn the distance, in this case, between Obama and Macron. And by having the neural network learn a distance instead of a category, you then create a Euclidean distance on which, again, you can do clustering metrics to identify how far apart certain data points are, and with that also identify the specific individuals within the data set. And this also allows you to add new individuals to the data set. So the result so far is that we got quite accurate in being able to identify the seals, but the problem with metric learning compared to the previous 2 methods is that it needs a lot of data to generate a comprehensive embedding. So therefore, in this case, we weren't able to fully solve it with metric learning. And lastly, in this challenge, we also have the application. And I know some of you here are software engineers, and you were like, okay, you do these 2 things and build an application in 10 weeks. That's impossible. Well, it is possible. However, you just have to steal a lot or use open source. So basically, the requirements are you need to upload images, detect all faces, and then identify them, right? This is just the basic architecture. Nothing special about that. The fast API backend, front end, and Next.js. 2 databases, one for the images in S3 and one Postgres SQL database to have all the metadata. The only thing different from a classical configuration would be that you have ML endpoints here. So as you might know, machine learning has a lot of different types of compute capabilities and requirements. So you would want to run that on different types of machine, and therefore you split those off from your primary backend and make sure that you can have them as separate endpoints. So this is the design. So we built this full application. Here you can you can create data sets and upload all images. You can manage your data sets. And then something like this, where the researchers were able to like redraw the bounding boxes correct or remove them. This is not something that you would want to try and build in 10 weeks, but this is just a completely integrated open source framework that we integrated into the application. Well, something like the top 5 is not that complex. So in the end, we were able to do face detection, face recognition with multiple types of algorithms, and we then set out to solve the same problem for more different types of species. And by now, we have already done so for 2. So one for turtles, where you see that we're based on the geometrical patterns of the side of turtle faces identifying turtles. The interesting thing here is that it ended up being a light glue algorithm that worked best compared to metric learning. The reason that that's interesting is that light glue is a type of algorithm that's designed for stereoscopic identification of objects in space. Meaning in robotics, you often have 2 cameras and you want to recognize an object in both of them to be able to localize an object in space. The thing with that type of problem solving is that objects in space often have a very geometrical shape, like the turtle face shape. So that's likely why this algorithm worked a lot better. The AI for so here we have a basic animation of cutting out the turtle face, identifying the 2, and then being able to compute a match between the 2 based on the key points that we extracted with light glue. But for bears, a challenge that we're solving as we speak, so we complete this challenge in 4 weeks. We were able to already build a very good bear face segmenter based on Segment Anything, a model created by Meta. Here, we're likely looking into metric learning, because bear face does not have these very geometrical spaces. So in this way, we also learn a lot about the field of animal re-identification. And we try to apply this knowledge every time we do a new challenge in this space, like, hey, okay, if we need to detect patterns on a zebra, for example, we would likely go more the light glue route, where metric learning would be for predators that have front-facing eyes, would be much more likely to work well. So this is how we reapply that knowledge. And last thing on my list is to invite you guys all to become part of this. You can become part of Fruitpunch, of our community. You can become a hero in your own hero trial. As mentioned, the challenges take only 10 weeks. We, of course, have a week of preparation and finalization, and you're certified based on the skills that you showed in our challenges. So I invite you all to also become a hero of your own journey. And that's it for today. Have a very fruitful day.